Previously in the black model we looked at estimating the cost of hedging against interest rates increasing. Of course we could also look at the cost of looking at the how much we should pay for a put option, because if we take this example and work through the detail and estimate using the black model the cost of insuring against interest rates increasing, there's also an equivalent type formulation where we want to investigate the cost of hedging against interest rates falling. And we could imagine that circumstance arising where in the future somebody wants to deposit money, perhaps in 1 year's time, and wants to ensure that they're hedged against interest rates falling below 8%, and that the payoff they would receive would be equivalent to any rate, LIBOR rate or similar market rate, falling below 8%. Again, we have to specify in a similar fashion the principle involved, the exercise, the quarterly rate, probably expressed as in terms of a flat term structure, and also sigma or volatility as outlined here. In market parlance, when you hedge against interest rates falling, we tend to refer to this type of option construct as a floor or flooret, which is really a put option. And so we had worked out this detail as a call option. We had set it up in Excel, and we had worked out in terms of a decimal the cost of hedging against interest rates rising, and on a $10,000 principal with those parameters, we found that the cost, the cash amount, was $516. For a put option where we're hedging against interest rates falling, we would be more interested in working out a put option, and the put option would take this form here, but otherwise the D1, D2 would be estimated in exactly the same way. So there's two ways of approaching this. One is using put call parity and expressing the put first of all in terms of the percentage. So if we work out C as being the 0.0026, as we would have seen in terms of the option, we would have seen the 0.00206 and then multiplied by 10,000 and take the difference between the two time periods, 1.25 years and 1 year. That was $5.16 for the put option. We take that call value, express everything in terms of its decimal, and then we would write P is equal to C plus K minus F, or the exercise minus the future rate, and then discount at the risk-free rate at the 1.25 years, or T2, and that's as a decimal. P would be equal to 0.01. So in setting that out then as the put position, we could express the formulation in terms of its VBA, so we could investigate the call here and the put in terms of the cash amount, and in terms of the decimal. So okay, so let's look at the VBA code here that we might use. And for the call option, as before, the black call or the black cap, again we have 2 time periods T1, and we discount at T2 because the payoffs occur at 1.25 years, although the difference in rates that we use for estimating the value of the cap is at the shorter time period of 12 months or 1 year. Likewise, for the put option, we can write this in exactly the same way, except we must write D1, D2 expressed exactly the same way, but for the put option, the payoff should be estimated as E negative R times the longer time period multiplied by the exercise ND negative 2 minus F times N negative D1, where N denotes the norms, or the normal cumulative probabilities. Okay, so let's look at that for a moment. Both using put call parity or using the black model. Okay, the value of, if we just express in terms of decimal, the value of this is 0.01123, and that's the same as what we have here. When we multiply by the cash amount, principal, the proportion of a year that the loan or the depositing term involves, as a cash amount, that's 2808. Okay, so whether we use put call parity or whether we use the black model, we arrive at the same decimal amount, and then afterwards we multiply by the principal involved and the proportion of a year involved, and that's how we get that 2808. If we were to set this up in C++, using Xcode, we could use the following code. Let's observe this for a moment. So I'll just copy the relevant code. I originally took this code from flooret, and I've adopted or modified a bit so that the black Schultz model becomes the black model for a cap or floorlet. Okay, so let's take Xcode as being our C++ compiler, create new project. That might take a second. I want to create an application command tool, so next, and it's black, we'll call it black cap floor because it's the black model, black 1976 C++. Okay, so next, so it's black 1976, and we'll save this in desktop. Okay, we'll just save here for the moment, create, and then we look to our main, and okay, so we can take this code out here and paste in the code that I had initially. Okay, so this is in effect, it's flooret type code, and some issues seem to arise here, so we'll just check to see what's the origins of this. Okay, so we seem to have some issues in terms of given functions, pi and so on, have been recognized. Okay, so we put in, we can copy and paste, edit, copy, paste, and we include another library, and we can go math, so math H. Okay, and okay, that seems to resolve most of those issues, and then we can come down okay, so I'm going to use the same as before. I'm going to use the same code, but now we don't need system pause because that's a Microsoft command, and we can leave this out as well. So that'll give us a little bit of extra space here to observe what's going on. But in effect, what we have here is the black model, and so it's a black, the function's name, okay, black CP. The normal cumulative probability is being given by this functions, which has to be incorporated into the program, so we don't call up a norms dist, which is typical in VBA. And the workhorse is, well, we calculate D1, which is what we would have observed before, and the call option is E, or the longer time period F, D1 minus K N D minus sigma square root of T1. So D1 minus sigma square root of T1 is the same as D2. And I use to get the cache amount, we take that call, which would have been a decimal, and then we scale it by the principal involved. So we scale it by the 10,000, which we set down here, L equal to 10,000. So same parameter inputs as we have had in our PowerPoint. So we're using the same type of parameter inputs as we used initially. And okay, so let's take for a call option, and we know the answer here must be equivalent to $5.16, and we know that the put option is 2808. So let's just verify those results. So we'll run C first. And that takes a moment. And the build has succeeded. And we get the black model call is 5.16, so the cost of setting up buying insurance against interest rates increasing above 8% is 5.16. If we change our C to a P, we convert the Caplet into a Floorlet, and we use put call parity. So if it's a call, if otherwise, if this is not C, we have P, then we use put call parity. So let's just run that. And the value here for the put is 2808, and that seems to correspond with the values that we have here for the call and the put. Okay, so we obtained the same results in both instances, and this code looks as if it is a viable code then for estimating the cost of purchasing insurance against interest rates increasing or interest rates decreasing, and we're implementing the black 1976 model for both the Caplet and the Floorlet.